Hello and welcome to this Maxis lecture. Now, I know last video I said that we are going to do AC circuits, and yes, we are going to do them, but first there are a couple of videos that I want to do beforehand that I found them very important as well. And one of them is magnetic circuits, and the other one it's about the multiple types of sinusoidal waves. And sine waves are the waves that we use inside AC circuits, but there are more types. There are also square waves, there are also triangle waves and staircase waves and more types of waves. So we are going to do a video about waves as well before we do the AC circuit video. So we get familiar with the type of sines and how to calculate a wave. But anyway, this week we'll do magnetic circuits. And as you can see, this is one of the papers that we prepared. But before anything, let me show you how a magnetic circuit looks like and why it's different from a normal circuit. There you go. This is basically a magnetic circuit. So a magnetic circuit is basically a ring or a square or whatever shape you want to be of metal. And in this case, it can be also combined metal. For example, to be iron, steel, and cobalt inside of them. And through them there is a coil of wire like an inductor turned around it, and it's got many turns as well. For example, this one has 10 turns inside of it, and the magnetic force that we are interested in this circuit to find out is determined by the current going through this ring. So basically, the higher current, the higher the magnetic force, and the lower current, the lower the magnetic force. And this circuit type is very different from normal circuits because it's got new variables and new factors that we need to consider. However, it can also be very similar to normal circuits. For example, and as I show you as we do the problems, these magnetic circuits can be simplified in normal analog circuits that we're familiar with, and many of them have the same properties as well. But we'll learn more about it as we go. This is the introduction, so yeah, let's get started. First, let's read what I wrote here. That is, magnetic circuits are very similar to analog circuits. They have their own equivalent of E, which is the voltage source, I, which is the current, and R, which is the resistance. And we'll see them. For example, when creating a magnetic field, magnetic fields like inside the inductor from the last video, then there are three main values inside the magnetic field. First of all is flux density, and flux density is very similar to current. Flux density is equal with B, which B is measured in Teslas, and then that would be equal with the flux density over the area. So there you go, flux density, which is calculated in Webers, and the area. B Teslas. Sorry about that, somebody just worked inside the room. Anyway, so yeah, B it's basically Webers, which is this value here for the flux divided by the area, which is meter squared, and that will give us the value of Teslas. So B it's named Teslas. Anyway, and the flux density, the flux, it's an equivalent of I inside the magnetic circuit. Okay, now let's go to magnetomotive force, or MMF simply. This one, the magnetic force, which is this one here, it's a replacement for E, which is the voltage source. So in a magnetic circuit, instead of having a voltage source E, they have this squiggly F and called MMF. Okay, and F, the magnetic force, is equal to amperes per turn, number of turns, and number of amperes, which is the current I basically. So it's N times I will be equal to this one, to the source, to the MMF. And permittivity. Permittivity basically is the resistance inside inside the magnetic circuit. And you can already get familiar to this formula because this is the same formula we use inside an inductor. Basically, you got like the total permittivity, you got the permittivity of the material, and then we got the permittivity of the air. and micro r is the permittivity. Okay, let me just go on this side here. And also I wrote them here as well, so it's simpler for you. In a certain electric circuit, we have EIR, which is the cause, effect, and opposition. Cause, if the voltage causes a movement, I is the effect that is created from the movement, and R, the resistance, is the opposition, and it's the same for this one as well. The squiggly F, the O, and the R are like these values, they're basically. Anyway, okay. Reluctance, as I said, is that special resistance. Oh no, permittivity is not the resistance of the material. It's basically permittivity. Reluctance is the resistance of a material. Anyway, and here it's also something called the Ampere's circular law, which is basically Ohm's law, you know, as voltage, voltage is equal with current times resistance. We have the same one here as well. MMF, it's equal to flux times reluctance. Anyway, and what we want to know is the magnetic force as well. This magnetic force, will help us find this quickly H. Will also will help us find the B value, which is basically the flux density, and that flux density will help us find the permittivity of the material as well. Basically, the magnetic force is like the power inside a normal circuit, you know, and it's important to know it, like to find out, to know a number of variables, you know, in case that you don't know one, you can like track back to it. Anyway, Ampere's circular law, as I explained, it's like Ohm's law when it comes to the MMF and the equation, and MMF and how to find it out, which is basically the number of the turns of the coil multiplied by the current going through it. And that's I'm saying that with the current in the circuit, that's how you determine the power of the magnetic field. Magnetic force. Because as you know, like in a circuit, realistically, it's easier to change the current than to make a system that adds turn to it, you know, or that changes the metal. But anyway, and here it's one of the rules, as a flux line want to be as short as possible, and they will take the path with higher permittivity. Okay, that's important to know. We won't really use this rule in calculations, but so just you know. And there can also be air gaps, like you can create one of them like this one here, and instead of having a metal in here, you can have a small gap in here, and the flux will still go through, like in capacitors or in inductors, really. Something similar to that, but it's got a special formula, and for it you need to take in account the permittivity of air, really, and here is a shortcut of the formula here. And the gap has to be quite small, actually. If it's too big and there is not enough flux to go through it, then yeah, it won't create any magnetic force then. So then that will make it a kind of useless circuit, you know, if it doesn't have magnetic force. Anyway, but how do we determine the Teslas? Like, yes, maybe we know a few values, but what if we don't know all of them? Well, there are two graphs that we'll use today as well, very useful graphs. One of them is this one here, and this is the other one. Don't worry, they are basically the same thing, which, if you are curious, it shows you the value of Tesla's B here, and here is the value of H, of the magnetic force. So by determining the magnetic force, we can also determine the value of Tesla's, and that these graphs will make our life easier, because we'll simply find the value of H, which is the magnetic force, and from there on we can easily determine the value of the Teslas. And if we determine the values of the Teslas, then we can easily find the flux inside the circuit. And of course, if we know the flux, then we can determine like the current needed as well. So there are many ways to tackle these problems, really, like any normal circuit, you know. So after I saw this, I'll keep this graph next to me. I'll keep some of the formulas as well, and we should get started on making them. on solving some problems so you understand how to do them. Because just explaining doesn't really, I don't think you understand from just explaining simply. That's why I do so many problems, because by doing problems and doing like various ones, like with something adding on to them, making more and more harder, then you will more and more understand them. All right. So, sorry about this. I should have reversed. I should put A and B. I was thinking that maybe it's easier to calculate it first and then draw the circuit, but then I realized no, it's actually easy to draw the circuit first and then calculate it. So let's start with this one, which is very simple. So let's draw the circuit. So as I said, these metals act as resistors because they create reluctance, which is this one here, reluctance. And they are basically the resistors. And the flux will be the current. And the flux basically, it's like a normal wire. It will go through one direction only throughout the metal. That will be our flux. And F will be this one here, will be the number of turns multiplied by the current inside. Okay, so let's draw the diagram. So we make one big circle here, we put the special F in here, then we put this direction, we put one wire with one resistor here, one resistor here, and one resistor here, then we close it. And then we point the direction, so that will be the flux, flux being the current, and magnetic MMF being the source. So here is the source, here is the flux. Now let's put the reluctance. So this is the first R for iron, this is another R for steel, there is another R for cobalt. There you go. So that's how you translate a magnetic circuit in a simple analog circuit that you can see and you can understand. And they also have the same rules. For example, if you do VR1 plus VR2 plus VR3, it will give you the total voltage in here because the current splits inside the resistors. Well, it's the same for MMF. You can calculate the MMF inside each component, each metal type, and then get the total MMF from the source. It's just like normal circuits, really. All right, so now let's do A, which will be theoretically the second one, which is find the magnetomotive force in each material, or MMF. So we have to find the MMF inside the iron, the steel, and the cobalt. Well, how do we start? Well, we have everything we need to know here. Basically, I gave myself all the information that I need. So we know this coil has 10 turns around it, so there are 10 turns inside, and there are 30 amps going through it. And from the formula here, from up here, the circuit formula, MMF is equal to the number of turns times the current. So let's put the special F equal with N times I. That one will be equal to 10 times 30. That one will be equal with obviously 300. Alright. MF. There you go. It doesn't have a symbol. I don't think it does have a symbol. Let me check. MMF. Oh yeah, it does. It's got 80 as a symbol. Okay, let's put 80 then. 80. There you go. Alright, let's keep going. So we know MMF inside the first one. What's our next step then? Well, our next step is to find the values of in the materials as well. So how can we find the MMF in each material? Well, basically we apply the magnetic force multiplied by the length. And you may wonder, well, how do you know that? Let me write here. So this one is equal with L times H, and this one will be for iron. Well, how do you know this? Well, basically we have here the formula for the magnetic force, and we know that magnetic force H is equal to force over divided by the length. So we can rearrange this formula and make it the force, no, the MMF, magnetic force, no, not magnetic force, MMF, it's a magnetomotive force. It's equal with H, the magnetic force, multiplied by the length. And that's why we rearrange it. And we'll do so for each material. So, and also we add them together because like in a normal circuit, they are in series, so we can just add them together like normal resistors. L times H steel plus L times H cobalt. And I gave myself all the values that I need, so we just need to replace them. For example, in iron it's a length of 2 and there it's a magnetic force of 80, so they need to be equal with 2 times 80. For steel it's 1 times 50, and then for cobalt it's 3 times 30. Okay, and then therefore all of it will be equal with 300, and that will be equal with 80 plus 50 plus, no wait, that's 160 plus 50 plus 90, and that will be equal with 300, yeah, basically. And that proves that the answer is correct. So answer is correct, because like imagine this being volts instead of 80, you know. If this was volts and each resistor had this value of volts inside of it, we know it's correct because it matches the voltage source. Well, here each resistors, not resistor, each metal has its own it's called MMF going through it, and all of their MMF combines gives this megamotive force, as this is the same number as the force that comes in. So we know this is correct and that our calculations are correct. And another rule is that we can actually apply node analysis in here as well. Like you can pretend there is a node in here and there is a node in here. And let's say if you want to find flux A, which will be flux at this point, then you basically will do flux B because it's going out and flux C because it's going outside this point. We just put them as positives. However, in point B, for flux B, this value flux C is coming inside while the flux A is going outside. So the ones that are going out are seen as positive, so flux A is positive. However, the ones that go into this point are seen as negative values. So we can apply node analysis for this type of magnetic circuits as well. Okay, so you may wonder, like, what's the point of this exercise? Well, this is an introduction really, so you can see how a magnetic circuit looks like and how to transform this in a analog circuit to have a better view of it and a better understanding, and how to determine their MMF, which is their voltage source kind of, by doing the number of turns times the current, and how to find the other values such as the flux or as we see here, the MMF through each metal. But usually when you do a problem, the value that you want to find to discover is I, which is basically the value of current. Okay, so let's go to an exercise now. Okay, so this is the problem. The first one that I will do, it's a pretty simple one. We just made it in like a circle shape. You know, I try to fill it in here like as this is a hole. So the flux will go in this direction. You know, it's got only one direction it can go. And the values that we have been giving is that the area is equal with 2 times 10 to the minus 3 meters squared, and the length is equal with 0.2 meters, and that is made out of cast steel. And there are 500 turns, basically there are 500 curl turns around the ring, and that's everything we know about it. Okay, and what's asking us? It's asking us to find the value of I if the flux is equal to 4 times 10 to the minus 4 Webers, and B, what is the value of the permittivity of the material and the total permittivity. And the last one is draw the magnetic circuit. Well, we'll start with drawing the magnetic circuit. So let's do that first, which will be the source, which is this one here, squiggly with F in this direction, and then there's the wire, there's the resistor, which is basically the material it's made out of. There you go, and it's closed. Then the flux goes in this direction, and here this one is like an R for made out of cast steel. There you go. Okay, so how do we start? Well, first we start by finding the Tesla value. Well, what do we start with the Tesla value? Well, we know the flux, which is this one, and we also know the area. So finding the Tesla value will be quite easy because we just apply the formula flux divided by area. So let's write it here. A, and we do flux over A, it's equal with B. Then therefore B is equal with 4 times 10 to the minus 4 divided by the area, which is 2 times 10 to the minus 3. There you go. And that will give us 0.2 Teslas. Okay, and now, well, what do we do? Because we cannot really find any other value here, you know. I mean, yeah, we find the flux density, but we can't really use it for anything else since we are missing parts of the formulas. Well, as I said, we are going to use the table as well. And because we know the value of the flux, yeah, which is this one, this line here, this is the Tesla, the flux density. And this one will be the value of the magnetic force, H. All right. And we know that we have 2 Teslas, which is this line here. Let me get a ruler. Actually, it to be easier to point out. So we got the 0.2 for the Teslas from the calculation. And we know the material, it's cast steel. So cast steel is this line over here. So all we have to do is to align them. Basically, there you go. Put at the point of 0.2, be at that point there, and then we just do this. And we'll find the approximate value. There you go. And I'll say, because each square it's 20 in this one, I would say it's about 20, 40, 60, around 70. Because it's at around it's around 3.5. All right. So from the B versus H graph, we determined H is equal with 170 80 per meter. So that is the magnetic force, 170. And this opens a lot of opportunities now because we can find the current. If we go to the magnetic force, there you go. Here we have a formula. Magnetic force is equal with the number of turns multiplied by the current divided by N, basically. So we can apply this formula because we know the number of turns being 500 and we know the magnetic force being 170 and we know the length because length is equal to 0.2. All right, so let's get started. So we rearrange it. So instead of putting H is equal with N times I divided by L, we rearrange it in I. It's equal with H times L over the number of turns N, and that will be equal with 170 multiplied by 0.2, isn't it? Yeah, 0.2. All of it divided by 500, the number of turns. and that will be equal with, so let me get my calculator quickly. There it goes. That'll be 170 times 0.2 all divided by 500. That'll be equal with 68 milliamps. 68 milliamps. There you go. So now we did the first criteria, which is basically finding the current that will give us this flux of 4 times 10 to the minus 4 Webers. And we need to apply 68 milliamps to the circuit to get this current. And now you can see why it's important to know magnetic circuits and why we usually calculate the current, because the current is the easiest value to change in a circuit and it's really easy to connect it to it, you know. So yeah, this is how you find the current, at least in this first problem. Of course, they'll get more and more complicated as we go on. Now let's go to the second question, which is what is the value of micro and micro R, which is basically the permittivity. Well, let's look at the formulas for permittivity. There you go, that's one of them, which micro R is equal with micro U divided by micro O. But are there any other formulas for permittivity? Because there should be one more. And oh, there it is. The magnetic force is equal with the permittivity of the material multiplied by the H, which is basically the value seen in the graph by H, yeah. So we can rewrite that one as B is equal with micro permittivity multiplied by H, and we rewrite this one as permittivity is equal with Tesla's divided by H, which is the magnetic force. There you go. And then we just replace those values, so this will be equal to 0.2, which is our Tesla's, divided by 170, which is our magnetic force, and that will give us 1.176 times 10 to the minus 3 Webers per area multiplied by meter. There you go, that's how you write it at the end of it. And now we need to find the total permittivity, and that'll be micro R is equal to micro over permittivity over permittivity of the air. And from the inductors we already know what the value of the permittivity of the air is, which is basically, wait a second, let me rewrite this one, which basically is 4 times pi times 10 to the minus 7, and that will give us permittivity of 935.83. And there you go, we found the current and the permittivity inside this circuit. And if you want, pause the video and take a picture or a screenshot of this how's it called, graph over here, because it's very useful. It's a big part when calculating the magnetic force, because it easily helps you with determining it. Maybe there's another way of calculating the magnetic force, or like better ways to do it, but this is the way that I like to do it. For example, another way to do it, to calculate the magnetic force, is to divide the normal force by the length, but divide mmf by the length. But usually we do not know the value of mmf, because we try to find out the current, find out what current is required to get our desired flux going through it, or our desired magnetic force. Sorry, I took a sip of water. Okay, I will pause here and we are going to go to the next one. Alright, so welcome back, and this will be magnetic circuits with two reluctances, which is basically two different metals inside of it. However, you'll notice something different from this one. You'll notice that we do not have the length in this magnetic circuit. No, instead we have the length from this side to this side. We also have the length from this side to this side, and the length from this side to this side here. And we'll need to calculate our own length, and I'll show you how. But first, and also we know the area of it, and we also know the flux going through it. Now, I would say that the first thing you usually do, you may think the first thing we do is to draw the magnetic circuit equivalent of a how is it called, the analog circuit. But no, we won't do that yet. First, we will mark out what we want to know about this magnetic circuit, and I'll teach you how. Basically, first thing you mark up is the direction of the flux, as in the direction of the current usually. So the flux will be in this direction. It will go around there. So it's got only one direction going through it. Okay, and then the next thing I want to do, which is separating the metals for you really. So I'll make these steel sheets purple. I'll like do this purple crossing around them so that you see. And then for the other one, which will be the, just a second so I can close it, which will be the cast iron, we'll make it with blue. There you go. So now we can see the triangles between them. And a big part of solving these problems is to know the length. So next step, we'll calculate the length. You may say, well, the length is just this value plus this value plus this value, just the square and the size of the square, and that's it. But no, it's not like that. It's important to know specifically the length for each one of them, the length of the cast iron and the length of these two, which is the steel sheet. Okay, so let's start with by marking the points. So we'll mark this corner as A, we'll mark this corner as B, which is basically the corner with the line here, We'll mark the down corner C, we'll mark this corner here D, we'll mark this one E, and we'll mark the last one as F. There you go. So we marked the points basically. And this will be very useful because we know from point F to point E it's 4 centimeters, and we know from point E to point D it's 5 centimeters. And this will help us write it in a way that's understandable. And what do I mean by that? Well, let's first ignore these questions first, and let's determine the length first. Let's say the length of A, B, E, and F, these 3M. So the length of A, B, E, and F will be equal with the length of A and B, which is this side here of the shape, plus the length of E and B, which is this side here, plus the length of F and A, which is this side here. Oh no, sorry, I'm sorry. E and F is not E and B. It's this side here, this length here, plus the length between those two, plus length of F and A. But if you do basic geometry, you can already see how you calculate it. You basically just calculate the length from this point, which is this red dotted line, with this point, which is this dotted line, with this point, which is this dotted line. And we know that from this point here to this point here, from here to here, that will be 4 centimeters. And from this point here to this point here, that will be 4 centimeters. And because this is square, we know that this 4 centimeters, this length of E and F, it's the same as the length of A and B. And the length of F and A, it's equal with this length here of 4 centimeters. So then the length of A, B, E, and F will be equal with 4 centimeters plus 4 centimeters plus 4 centimeters. That will be equal with 12 centimeters. And there we go. We found out one length. We found out the length of the steel cast steel sheet steel. So L of sheet steel will be equal with 12 centimeters or 0.12 0.12 meters. There you go. Now we need to calculate the length of this material right here. So the length of BCDE, it's equal with the length of DNC plus BNC, so L of BNC plus the length of D and E, and then all of it will be equal. We know from this point to this point it's 0.5 centimeters, and we know that E and D it's the same as B and C, so it's like 0.5 plus 0.5, and we know this point here D and C it's equal with 4 centimeters, so plus 4, and then all of it will be equal with 5 centimeters. So then the length of cast iron will be equal with 5 centimeters or 0.05 meters. So there we go. We find out the lengths inside the magnetic circuit. And that's a very first and important step to do. Before doing any calculations, it's important to know the length of it. Alright, now let's read what it's asking us. Find the magnetomotive force MMF for each material. That's the first one. Then find the current I, and then draw a circuit diagram. First we'll draw the circuit diagram, then we'll find the MMF in each material, which is inside the steel sheet and the cast iron, and then we'll find the current. Okay, so let's draw the circuit. So it's got only one source, which is this one here with the coil. So one squiggly F in this direction, and then it's got two special resistors, and the flux is going in this way. Y2 reluctance, reluctances, was because one side is made out of cast iron and then the other side is made out of sheet steel. So there are two materials, therefore there are two of them, cast iron, and the other one which is sheet steel. There you go. And this is basically the analog diagram of this magnetic circuit. Okay, that was nice and simple. So let's keep going. What our next step is? Well, our next step is to find the value of Tesla. And basically that will be, let me mark this one as A. Basically that will be B, the formula equal with flux divided by the area. We know the flux as being 3.5 times 10 to the minus 4, and we know the area as being 6.452 times 10 to the minus 4. Okay, so 3.5 times 10 to the minus 4 divided by 6.452 times 10 to the minus 4, and then that will give us a value of 0.542 Teslas. There you go. And now we will need to use the graphs. So why we need to use the graphs? Well, we need to use the graphs for both of them. For H steel and the H for cast iron, and obviously they are based on approximation. Okay, so let's get our nice paper. Oh no, yeah, this one should go up to where we need to go. And we have this line here is for the sheet steel, and this line here is for the cast iron. No, this one here is for the cast iron. So we know the Tesla, by the way, the Tesla value is the same for both of them because it's determined by the total area, like the area of the shape, and it's also, let's focus, and also it's determined by the flux of the shape, So yeah, basically this is this will stay constant no matter the material. It can be like 20 materials, but if all of them has the same area and the same flux, then yeah, they don't matter. Okay, so let's go here. So that was like 5.42, so let's say it's like 5.5. So and 5.5 will be about here 5.4. So the first one, it is this one, the sheet steel 5.4. It will be at this point here. So then it will look straight down from it, and that will be around here. There you go. And what is that? So it's like 20, 40, 60, let's say and a half, so it's like 70. Okay, so for the sheet steel to be equal with 70, 80 per meter, area teslas per meter. Now the next one is cast iron, and cast iron will have a higher magnetic force because, as you can see, it's steeper as it goes up. So that'll be 5.4, which is this one here, and we align the ruler. Oh dear, actually it's not on this one. The cast iron value is not high enough. It needs to get even higher, so we'll have to use the other one, which is this one here. Okay, so 5.4, so that'll be, maybe it's 2 by 2, isn't it? So I'll say somewhere around here maybe. Yeah, that looks okay, I think. No, it's here. No, it's actually here. Yep, that's the one, I think. So let's say it's somewhere around here. So let's say that's 0.5 at the middle, 0.4. So now we'll look from this position down. So I think that will be, I would say it's around 160, because like every 5 ones is like a value of 200, and it's not at the half of it, it's only 2 squares away. They are 300, so 300 divided by 5, what that will give me, it doesn't matter, it's 1600. There you go. So H, the magnetic force inside the cast iron, will be equal with 1600 area teslas per meter. That's quite a big difference, isn't it? Yeah, you can already see how we can manipulate the the magnetic force really in like different sections of the magnetic circuit, because obviously this will emit more magnetic force than this one here, so you can kind of limit it by the material that you use. Anyway, okay, so that was the first step and the second step. Now the third step is to determine the MMF inside each material, because that is what the question asks us. It's not asking us to find the total MMF, it's asking us to find the MMF in each material. So we know the magnetic magnetic force, so that will be easy to determine, because it's basically the magnetic force multiplied by the length. So let's say this one for sheet steel, it's equal with the magnetic force H multiplied by the length. And we know that inside this, the length of this steel sheet, it's equal with 0.12. So that would be 70, which is the magnetic force. There you go. Multiplied by 0.12 in meters. It's very important to convert it from centimeters to meters, or whatever value you have. You always have to be meters when calculating. And that would be equal with 8.4 area per teslas. And there you go, we found the first MMF. Now let's find the second one for the cast iron. So MMF for cast iron, it's again the same formula. Basically it's H multiplied by L. That will be equal with, there are 1600 magnetic force multiplied by 0.05 meters, which is basically the length of it, 0.05 meters. And that will give us 80. And there you go. It didn't make a big difference, but even the length makes quite a big difference as well, The smaller the length, the less mmf it gets inside. So now we can calculate the total mmf by simply doing squiggly line. It's equal with the squiggly line of steel, let's just call it steel, plus the squiggly line, because they are in series, of cast iron. The outbound will be equal with 8.4 plus 80, and then the total one will be 88.4 AT. And there we have it. This one was for A. We found the mmf in each one, each material, and also we found the total one. And because we find the total one, question B is asking us to find the current I. And now we can easily find it from this formula right here. Right, second. This formula here. mmf is equal with the number of turns multiplied by the current. So let's write it down. So mmf is equal with the number of turns multiplied by the current. And we know the current, the mmf being 88.4, and we know the number of turns as being 100. So number of turns is equal with 100 multiplied by I. Therefore, I is equal with 88.4 divided by 100, and therefore I is equal with 0.9 basically amps. And there you have it. To get this flux value here, we will have to use 0.9 amps to go through it. There you go. Okay, so this one was another exercise. I will pause here and we are going to go to the next one. Hopefully you understand how to calculate the values, yeah, when there are multiple resistors, kind of, when there are multiple materials. And I hope you understand the steps, because basically first step is to draw the flux, which is going in this direction. Second step is to do the dots for each material, you know, where the material starts, each corner of the material, and where it ends. And then, very importantly, the third step is to calculate the length of each material. After you calculate the length, the only thing we'll have to do, sorry about this, the LED went off. Okay, the only thing we'll have to do is to calculate the Teslas and to use the graphs that I showed you earlier, you know, these graphs, to find the magnetic force. And after we find the magnetic forces, we just find the mmf in each material, and after we determine the mmf in each material, we can find the total magnetomotive force, the total mmf, and by doing so we can easily determine the current. And this is one way to do it. Hopefully you understand how, and don't worry, we are going to go through more complicated circuits as well, but I hope you see the similarities between this and analog, and you understand the differences. The differences being the need of calculating Teslas, and that the need of using the graph of the materials to determine the magnetic force. All right, I'll pause here and then we'll go to the next one.